Good morning. This is Dr. Barrows, and we're going to do the makeup lecture for last Friday. And my daughter is doing better, so things are good there. All right, first up, we're going to take a look at the PLQ that I assigned on Wednesday. Question number 1, we're looking for the true statements. Number 1A, or the first answer, is not true because s orbitals do not have lobes. S orbitals are always spherical. A 2p orbital is always lower in energy than a 3p orbital. And this is because the principal quantum number 2 versus 3 indicates that the 2p orbital on average is closer to the nucleus than the 3p. A picture of an N1 Bohr orbit would look the same as a picture of a 1s orbital. And this is not correct. The main reason this is not correct is that when we take a look at the Bohr orbit, that was a specific path around the nucleus in the hydrogen atom, whereas a 1s orbital is a region of space. And so the orbit in the Bohr we showed in class as being more like a circle or concentric circles if you looked at multiple values of n, whereas when we take a look at the 1s orbital, that's going to be a sphere. One orbital can hold up to not 8 electrons, but a maximum of 2. And the d orbitals don't always have 4 lobes. Most of them do, 4 out of the 5. But there is one that is something like that. So that is not correct either. Moving on to number 2. Please assign an orbital designation to each two-dimensional representation. Answers may be used more than once or not at all. Well, there are a variety of different answers here because I had to change the question about halfway through. WebAssign was being extremely picky about 3D as to which option of 3D you chose. If you don't know what I'm talking about, that means you probably answered one of the later versions of the question. But what I was looking for is that 1A would have been best described as a 1s orbital. E would have been best described as a 2s. D is a p orbital. And then both B and C are different types of d orbitals. Moving on to number 3. Match the quantum number with the property that it determines. Well, first off, n is always a determiner of energy. L is definitely a determiner of shape. And n and L as a combination determine energy when you have more than one electron. Because when you have more than one electron in an atom, whether or not one electron is in the s, p, or d does matter. So s, p, and d do have different energies if you have 2 or more electrons in an atom. The m sub l is always going to give us orientation. M sub s is our electron spin. And that's basically used just to distinguish between 2 electrons that are in the same orbital. On 4, it says identify the sets of quantum numbers that correspond to an electron in a real p orbital. Select all that apply. Well, the main idea here is that when we're looking at p, we're looking at L of 1. So if it's not L of 1, then it's not correct. So this is not correct. That's not what we're looking for, but the others are. Now we need to go through and see if this realness characteristic, and this just means is it a possible combination of quantum numbers. And so when we look through here for the first one, L is less than N, so that's a potential. Same is true for the third one. And the others as well. So that criterion didn't help us too much. But we need to take a look at the M sub L. Remember that M sub L is constrained by the L value. So this is the positive, negative L, and then the numbers in between. So if we look at this, the first one, 0 is between +1 and -1, so that's okay. Third one's okay. This one's okay. This one's okay, but this one is not okay. -2 is outside the range of L equal to -1, 0, and +1. So on to question number 5. In question 5, we're going to be looking for invalid combinations of quantum numbers. So we're first going to look at any combinations in which N and L are incompatible. And so L must always be less than N. In the first case, second, well, here's an invalid combination in the third. There's no way N can equal 0. The smallest value of N is equal to 1. So that's an invalid case. And the next one's invalid as well. L must be less than N, so it can't be the same as N. So that's an invalid case. If we look at the others, all of them appear to be valid cases. The next comparison we're going to make is going to be between L and M sub L. When we take a look at these, we're looking for values of M sub L that don't fit, that are incompatible with the value of L specified. So just like in the previous problem, we're going to be looking for values of M sub L that don't make sense, given the value of L in the problem. And right off the bat, we see that M sub L cannot be -3 if L is 2. It can be -2, and we'll just work our way down. M sub L can be 1 if L is 1. It can be 0. It could be 0. This one is not compatible because if L equals 0, the only possible value of M sub L is going to be 0 as well. So that's invalid. And if we take a look at these, it appears that there are 4 that are invalid. On Wednesday, we were looking at the box diagram. So it was our first introduction to this way of determining the filling order in electrons. And what might be useful is if you go ahead and take out a periodic table at this point and kind of follow along. This will be a bit of a review if you were present in class on Wednesday. On the periodic table, we can see that hydrogen has a single electron. And because one of the rules that we use for filling electron orbital diagrams is that the lowest energy orbital fills first, that electron is going to be represented by a fishhook arrow pointing up or down. It doesn't matter. But it's only going to be one, and it's going to start off in the lowest orbital. So the electron configuration for hydrogen is going to be known as 1s1. For helium on the periodic table, we have 2 electrons. Again, we're dealing only with neutral atoms for right now. And so we're looking at a helium atom, which has 2 electrons to balance the charge of the 2 protons in its nucleus. So its electrons are going to go into the 1s orbital as well and fill it. Recall that one orbital can hold a maximum of 2 electrons. Now, moving on to the second period of the periodic table, we're going to begin with lithium. And just like before, it's going to fill in order. So there'll be a 1s2, 2s1, beryllium, 1s2, 2s2. Boron, with its 5 electrons, one s2, 2s2, 2p1, sliding over to carbon with its 6. We're going to have 1, 2, 3, 4, 5, and now we have to decide where to put the 6th. And the 6th is going to go into one of the other orbitals. And it doesn't matter which one, and it doesn't matter the orientation. So just to maintain some flexibility, I'll put it over here. 1s2, 2s2, 2p2, and so on and so forth. So for nitrogen, 7 electrons, 1, 2, 3, 4, 5, 6, 7. Again, it doesn't matter if it goes up or down, as long as one is up and one is down, if they are in the same orbital. 1s2, 2s2, 2p3. Now, when we get to oxygen, we notice that there are going to be 8 electrons and no more vacant orbitals. 2, 4, 5, 6, 7, 8. So they have to pair up at this point. Now the energy goes up a little bit because we have more electron repulsion here. 1s2, 2s2, 2p4. For fluorine, with its 9 electrons, hopefully you're seeing the pattern here is that there's no difference in terms of the electrons taking a different route to filling. It doesn't really matter, again, if they're up or down, but it does matter that they're starting from the lowest energy and going to the highest. 1s2, 2s2, 2p5, and then finally neon is at 10. And the second energy level is full now. We'll go ahead and take a look at the third period of our periodic table now. But what I would like you to do is go ahead and pause the video and complete this in the notes. I'll go ahead and draw it in, but it won't be much use or it won't be very helpful for me to kind of verbalize this. So if you want to pause the video here, you're more than welcome to do so. I think I've done everything correct here. But what I want you to do is take a look at the pattern of filling here, especially between the period 2 and period 3. You should notice that there are some certain things going on here that really lend some both credibility to the quantum mechanical model as well as how the periodic table was determined from looking at chemical similarity. And so what we're going to do on the next page is we're going to look at some different types of things and then we'll come back to the patterns. Yes, writing out all those orbital box diagrams isn't a whole lot of fun after a while, but it's a good learning tool at the very beginning to get a kind of a visual representation of what's happening inside those atoms as we're adding additional electrons to an atom. But it does get tiresome. So instead of drawing box diagrams, we've been writing out those electron configurations. And so if we take a look at the case of aluminum, we have electron configuration that is 1s2, 2s2, 2p6, 3s2, 3p1. Or if we're working with selenium, it would look something like this. 1, S2, 2, S2, 2P6, 3, S2, 3P6, 4, S2, 3D10, and then 4P4. That gets old. So we are able to do what's called a shortcut configuration. And it's kind of similar in math where we can kind of group something together and give it its own variable. So for example, in here, and so what I'm going to do in here is I'm going to represent part of each of these configurations as another element. So what is this going to do for us? Well, by substituting in an element symbol, we're going to be able to eliminate part of this electron configuration. So in this case, the element that has the same configuration as the yellow block is that of neon. And then we add in what is left. 3s2, 3p1. Now we can only use noble gases as the shortcut elements. So for the example of selenium here, Se, we have to go back and look at the preceding noble gas. Remember, noble gases are the elements at the far right-hand side of the table. Argon, with its 18 electrons, is going to represent the 18 electrons that I have highlighted in blue. And that will save yourself some writing. So in class, we've been talking about ground state and excited state in relationship to electrons moving between energy levels in a hydrogen atom, and they can move between different energy orbitals in atoms as well. In fact, that's where all those other lines come from when you're dealing with elements that aren't just hydrogen. So for example, when we're talking about ground state, we're talking about the lowest possible energy state. And for magnesium, that's going to be a case where we have 1s2, 2s2, 2p, 6, 3s2. So notice that it's using all of its 12 electrons. Excited state has the same number of electrons. However, and this is the key point, in an excited state atom, it is not in its lowest possible energy state. So you might have an example like this. It's still magnesium, but it's magnesium that is capable of emitting light because it has excess energy. This would be another example. So again, it's 12 electrons, but arranged not in its lowest energy state. As an advanced hint for your exam coming up, if you looked at those two excited states, which one is capable of having a larger energy change? And then think about what will that mean for the type of light it can emit. Things to think about going forward. Now, some of you have seen this before in high school, and this is seeming pretty elementary. This seems pretty simple. Well, let's go ahead and take a look at a few here that are not simple. So just as always, we start off with the number of electrons. We're going to go ahead and put them in. And for scandium, that seemed pretty easy. Let's take a look at chromium. Okay, this is the chromium that you would typically get if you follow the energy filling rules perfectly. However, what you actually get is something like this. Now the immediate question is, why does that happen? And one thing that we notice in certain parts of the periodic table is that energetically speaking, it's better in some cases to take an electron out of a lower energy orbital to put it into a slightly higher energy orbital that's empty. Now, the reasons for this can get really, really complex. And I'm not going to test you on your ability to recall exceptions, but you need to be aware that they're there and kind of the properties that might lead to them. Let's go ahead and take a look at copper. So again, this is the copper you might expect to see, but it's not the copper that we see in nature. What you would see in nature is this. And so what we can infer from this is that pairing up the 10th electron in the 3D must have an overall lower energy component than having a 4s electrons paired. And then for zinc, zinc is what we would expect it to be. And indeed, the only places where we're going to see these exceptions are going to be in the transition metals. And again, that's part of inorganic chemistry. So it's something that we will not spend much time on in general chemistry. I'd like to go back to looking at the patterns that hopefully you saw coming out of the electron configuration diagrams. And notice that what happens as we go across a period of the periodic table. And so we're looking at the third period right now. And we can kind of ignore all the shortcut element here, which is all going to be neon. One of the patterns you want to observe is that different parts of the periodic table, different groups, different chemical families, have kind of characteristic properties. Remember, periodic table was put together long before any of this quantum mechanics came around. And so what we end up seeing is that over here are the alkali metals. These are the alkaline earth metals. These are the transition metals. Over here are our noble gases. And then right next to them are the halogens. Now, there are other names for these. There are the chalcogens, the pnictogens, and we'll talk about those more later. But for now, we want to see that as we move across a period, there's always a very specific order in which things go. The second pattern we want to notice is that within a family, within a chemical group, in this case the alkaline earth metals, and and hydrogen is just kind of one of the weird ones. It doesn't really belong in here. And so hydrogen is not an alkali metal. But the others do follow this pattern in which they all end in the same electron configuration, just with a different value of the principal quantum number. What this indicates is that there are different types of electrons in atoms. Some matter for reactions, and some do not matter at all. And so if we look at the sodium atom here, notice that what are bracketed out here are what we had assigned to a noble gas neon when we did a shortcut element. And the reason we can talk about them as behaving like neon here is that they have the same electron configuration as neon, and neon being a noble gas we know is not reactive. So the properties of sodium, the reason why it reacts explosively with water, come from this other type of electron. And so the two names we use are going to be core electrons. So you might see the term noble gas core, as well as valence electron. Now, the way we define these, I want to be very clear on. We define the core electrons as being those electrons that have the same electron configuration as a noble gas. So this noble gas is going to be neon. This noble gas is neon as well. This noble gas is argon. Now the valence electrons I'm going to highlight in green. And so the big distinction I want to indicate here occurs down in here. Again, the S and the P sublevels are those that have the valence electrons. Electrons in the D sublevel may or may not act like valence electrons. But again, that's in inorganic chemistry, which is beyond the scope of what we're talking about here in Chem 115. Now, as a final activity, I would like you to go ahead and complete this concept check. This will be part of the assignment that goes along with this video and notes. So good luck, and we will be discussing this on Monday.